Everybody sit down. Everybody sit down. Everybody sit down. You know what sit down means? It means not stand up. All right, so we're going to
this is mine.
Okay, take it. All right, so today we're starting a new topic, which is infinity, how large infinity is, and different sizes. Could everybody be a little more quiet? Hello. All right. All right, so we're going to do infinity today. We're going to do sizes of sets. All right, so this set, of course, contains three objects. It has an apple and a four and a chair in it. And those are finite sets. And, of course, an infinite. Could you guys do this later? I keep saying sit down, and that's what sit down means. All right, so an infinite set, of course, is bigger than any integer. We have the natural numbers, which are 1, 2, 3, 4, 5. Sometimes I include 0. I'm not sure whether it should be in there or not. And then we have fractions like 2/3. And then we have real numbers. And then the question are these infinite sets the same size, or is one bigger than the other? And Cantor came along. Where's Cantor? There he is. I don't know whether that's the year he was born or the year he did his work or died, one of the three. But anyway, he said that two sets have the same size if there's a bijection between them. And so then we can ask, well, you have the set of natural numbers and the set of even numbers. Is one set bigger than the other? And it feels like that the second set should be smaller because it's clearly half the size. But so half the size. But if you can do a bijection between them, you do from x to 2 times x. That's a bijection. Yes?
Define a bijection again.
Bijection is everybody over here is mapped to everybody over here, and everybody here is mapped back again. They're kind of paired up. They're paired up. So 2 goes with 4, and 4 goes with 2.
You could add up x equal to y for each x.
Yes, you can invert it. So what's Cantor? The lesson here is that Cantor's definition doesn't say that every mapping between them is going to be 1-to-1 and onto. It just means that there is such a mapping. So, and if this makes you feel uncomfortable, well, that's just the price you pay for looking at weird infinities. So here's another question: is the integers versus fractions? It feels like you should have a lot more fractions because, again, the integers are a nice subset of them. And in fact, the fractions are really dense. Between any two fractions, there's an infinite number of fractions. But we can't say for sure whether or not, we can say, we will say that there's a way of counting them. So how do you count them? It's natural to go sort of 1, 2, 3, 4, 5, and if you can map to each one, you can list them. You can list this one, this one, this one, this one, and if everyone gets listed, yeah.
So just to clarify, we're starting a new topic here.
Yes, this is a new topic. We're done with context-free grammars are done. We're now doing infinities. So So how do you count them? It'd be natural to count them like this. What's the problem with counting them like this? Is we'll go to infinity without ever getting to these other numbers, right? So I think some of you have seen this before. The way to count them is to go along a diagonal. I think you saw that how many of you have seen this in Pin 90 or something or other? 19. Some of you have, some of you maybe don't like putting up your hand. So this says that the two sets have the same size. Actually, and that says we say that the set of fractions is countable. Actually, we're overcounting because some fractions get counted twice, but that's okay. That just says that we're trying to prove that the natural numbers set is larger than the fractions, and this just makes that more so.
Wait, how do you count that? How's the pairing work there?
You just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Oh,
And here I'll show you again in the next slide, I think. How do you count triples, A, B, C? How do you print them all? Well, one way to print them all is this, where you loop over A, loop over B, loop over C, right? And is this going to get to them all? No, it's going to hit all the C's and never get to B equals 2, right? So another order is like this, where you first loop over the sum. That's sort of which diagonal you were on. And so this is doing planes instead of diagonals. And then you loop over all A and B and let C be the difference. Right? People kind of follow that? It's just doing diagonals. Or if you like 3 dimensions, it's doing planes. So the emphasis here is, though you're never going to list each tuple, at no point in time are all the tuples going to be listed because there's an infinite number. What is true is if you name your favorite tuple, it's going to eventually get listed, right? Eventually you'll get to the sum and then list it.
But Professor, what does sum minus A minus B mean?
That's the value of C.
Oh, okay, right.
Guess I could have said C equals and then plug C in there, but all right, so we say the set of tuples is countable. All right, so that's what we said before. A set is countable if it's smaller than the set of natural numbers, and
Can you go back on the sum? Do you give it the sum? The sum is what you give and your output to the C.
Sum is up here.
But is it what you give it to it and it outputs to C? Is it something that you...
I'm printing C. C is the value of sum minus A minus B.
The sum is what you're putting in. It's your input. The sum is your input.
I don't know what you mean. Sum is a variable here, and what we're printing is sum minus A minus B.
Iterating over like sums. Sums is just like...
Sum is which plane you're in.
So you're iterating.
Yeah. You're getting bigger and bigger planes. All right, so every finite set is clearly countable. It's smaller than the natural numbers. And if a set is also infinite, then we say it's countably infinite. So here's I did this in the morning, day before yesterday, and everybody got confused, and so I took out a little bit, few things, and made the colors. So what we're looking for is a formal definition here of what's needed. So we're talking about there are a number of different definitions. In fact, at one point I had 3 or 4 definitions, and I was converting between them, and everybody was getting really confused. So now I just brought it down to 2 definitions, and hopefully we can get them. So we'll say a set is countable if you can list all the items in them. And what does that mean is there's a function called list. There exists a list. And what does this list do? It's a function from the natural numbers, from the integers, to the objects in the set. So the list 1 happens to be empty, but list 2 is the apple, and list 3 is the chair, and list 5 is the 4. And so that's what our list is. And it's a mapping from the natural numbers to the objects. And what property do we want it? We want a property that for every object in the set, it appears in the list somewhere. And what does it mean to appear in the list somewhere? It means that there exists an integer that kind of hits it, that maps to it. Right? Everybody get that definition? So to say it again, one definition of countable is that you can list the items. And that means every item is in a distinct place. You know where an item, every location has a clear object in it listed there. It could be that some objects are listed twice. That doesn't do us any harm. But what is clear is that every object is listed at least once. Yes?
So it's not like a one-to-one function?
No, it doesn't need to be one-to-one. It means it's just you need that every object in this, the chair needs to be listed somewhere.
So is the list infinite?
It's definitely infinite, right? Because the integers go forever, and the point is that the set S is infinite.
Professor, can you go over the notation again? In English.
In English, so we say a set is countable if you can count them. Like people in this room are countable because I can list them. I can list her as 1, and him as 2, and him as 3, and him as 4. So for every integer, we know who I'm listing in that spot, right? So that's why it's a function. For every integer, I know what object I'm getting, what in that spot. And what's required is that every object, everybody in the room, is listed at least once. Meaning, for every object, every red thing, there exists an integer that gets mapped. You like the colors? I did the colors this morning. Yes.
Doesn't that also mean that it's unique, so you can't have that element for more than one index?
No, you could have 4 could also be mapped to a chair. And then it says for every object, say the chair, there exists an integer. It doesn't say it's unique. It could be 3 and 4 both mapped to the chair.
Professor, is it there exists an integer or is it an index?
Indexes are integers, natural none. Yeah, so when I say integer, I don't mean negative. Always assume I mean positive unless I get really excited and say we need to deal with negatives.
So an integer can't map to 2 objects, though?
No, exactly. Right? If an integer was mapped to 2 objects, then it wouldn't be clear that our set S was smaller, right? Because I could map 2 to everybody. Any other questions about this definition? I must admit it's good afternoons. I'm more awake in the afternoons, and you guys ask more questions in the afternoons. It was horrible yesterday. I was tired, and nobody was understanding a word I was saying. So here's a second definition. This is my favorite definition. In fact, I've never seen it written anywhere, so maybe it's Jeff's made-up definition again. But I would say a set S is countable if I can assign to every object a finite description. I could give it more than one finite description, but everybody has a finite description. And what's key about that finite description is it uniquely identifies the object. If I tell you the finite description, you'll know what object I'm talking about.
An index is a finite description.
Exactly. So for example,
1 is a finite description of her.
yes, exactly. She might not like the description, but it's a fine description, and he can be 2. She's number 1. Exactly. Exactly. So So, for example, some things might have infinite infinite descriptions. Like this guy here, he could be Herr, Doctor, Professor, Wizard, the great, 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 great. Right? So some things do have infinite names, but we could say, that's great, I'm going to just call you Bob. And then he has a finite description. Right? All right, so what are we saying up there? Oh, yeah, so apple, we could call this apple, we could call this Ford, we could call this chair. Everybody has a finite description. And now let's just sort of prove how it relates to our last definition, right? If you write the description using letters, then you can break the letters into individual letters, and then you can translate those letters into ASCII, and then you can concatenate the ASCII together, right? And that says each identifier is like a unique integer. That's right, and this unique integer uniquely identifies apple, right? So it's the same sort of thing as that we were doing on the previous slide. Does that make sense? The mapping goes the other direction. For every integer here, it's clear that this means 4, and it's clear that this means chair, right? All right, and again, we might not use all the integers, but that was okay. We were saying it was okay that you don't use all the integers. They have to be unique. You can't have 2 chairs, right? It's okay that you call this, sometimes you call it chair and sometimes you call it green star chair, but there can't be 2 things called chair. Right, so those integers are a subset of the integers, so that proves that size of S is smaller or equal to the integers. All right, so here's a proof, an easier proof in my mind, that the fractions are countable. Why? Why are the fractions countable?
Diagonal.
Yes, but an easier proof that the fractions are countable? Yeah, in fact, you can represent them as 2 finite strings, right? Here's a finite description of, and right, so again, you break it into characters and you break it into ASCII, and there you have a counting of them. Exactly. And similar, so this is the set of all finite sets of integers. So each of these is a finite set of integers, right? We're not having the set of all possibly infinite integer sets. It's a set of finite sets. Are they countable?
Yes.
Why?
It's finite.
They have a finite description. They're finite sets, so they have finite descriptions.
Well, what if you had a separate set that was 98 ... 23, 3. So you flip the order.
Oh, we're gonna exactly. So let's just do this. We get a name, right? Each one maps to an integer, right? But now what happens if we did a different order? Well, then it will have a different integer mapped to it, right? But it's okay for 2 integers to have the same name, to have the same object. An object can have 2 names. The key is that every integer is clear which object we're talking about, right? So given, I guess, I'm putting the commas in here too, right? So once you have this, you break it up in the commas and it breaks it up into a set. So it's the set's uniquely defined.
And if 2 sets are equal, what do we do?
2 sets are equal, then it's the same set. This is a set, so it'll only be in there once.
It's not like forbidden to put twice the same thing in a set.
Yeah, it is. Yeah, it is. That's the definition of a set. Is everything appears only once. Otherwise, it's a collection or a list. Yes?
You're saying a set of finite set of integers, so that the set of finite integers can continue as many times as it wants. So how are you saying that's countable?
No, they're not finite integers. They're finite sets. So each set only has maybe the set could have 1 billion things in it, but it can't have can't have an infinite number of things in it.
Yeah, but it's a set of that set.
Yeah.
Isn't the question that the set which includes like subsets?
Yeah, this is the set of all sets that are finite. And each finite set has a finite description. So hence the set of sets, a set of finite sets is countable.
That's like a rule, general law regarding this.
Yeah, general rule is that if every object in your set has a finite description, then your entire set is countable. So that's a good thing to write down. It will definitely be on some test or other, right? If you have a set that every object in it has a finite description, then the set itself is countable.
Can you repeat that once more?
Sure. Yeah, she can. She wrote it down in the notes. So.
Set that is every object in it has a finite description, and the set itself is countable.
Yeah, exactly. Thank you. All right, so here's another example, is the reals. Does each real have a finite description? No, each real does not have a finite description. It feels like a random real has an infinite description. In fact, if I keep flipping a coin an infinite number of times to tell you what all the digits are, it's very much, it takes an infinite amount of information to tell you what that random real is. So it feels like that the set of reals is larger than the set of integers. Everybody kind of buy that? And that's what we're going to do next, is we're going to prove that. All right? So how would you write a program that looped over all reals, that listed the reals?
We'll never get past one.
Right? Yeah, well, that's not a good argument, because you could say the same thing about the fractions would never get past 1. Right? But the fractions do get past 1. So we have to have a different argument. Yeah?
Because that right arrows.
This means that this set is way bigger than this set. Bigger, bigger, bigger. That's all it means.
We'll never get past 0.
All right, so now let's talk about uncountable sets. Right? We say a set is countable if there exists a list. Right? So a set is, right? Each integer is able to hit at most one element in the right? That's what we were. And if, right? I guess I should have had this earlier in the slide. The motivation is each integer is able to hit at most one object in the set. And if this can hit every element in the set, then the number of integers has to be greater or equal than the number of objects.
So for the reals, if you specify like 10 after the ball, then there will be like others that will have the same name but different continuation. That's why you have two different people, two different number have different same.
Yeah. All right, so a set is uncountable. Set is uncountable if for every list you give me any lists of the reals, then there exists a real that isn't listed. What does it mean for it not to be listed? It means for every integer it's not in the ith place. So here's our little object, the poor gnome, he didn't get listed. Yeah?
So, like, if your list, if you define list, and that list is a subset of the natural numbers, then it is countable.
Yes, if it's a subset of the natural numbers, then it's definitely countable. All right, so how do you prove this? Remember our first order logic game, right? We say, let list be an arbitrary mapping from the integers to our set S, right? We come up with an arbitrary, remember the adversary, we read from left to right, and the adversary sees the for all, and the adversary says, let list be an arbitrary list. And then I construct a a real number x from our set, and then the adversary gives me oops, that was funny. There we go. Then the adversary gives me an arbitrary integer, because he says, oh yes, what is he trying to say? He says, yes, I gave you this list, and x is mapped to something is mapped to x, and he tries to give me an I, which is mapped to x, right? And then I check, and I say, no, look at list I is not x, list I is something else, right? People see the proofs technique?
Can you go through it again?
Yeah. We want to prove that some set S is uncountable, right? So how do we do it? We say adversary is claiming, by way of contradiction, we assume it is countable, right? So we say, okay, if it's countable, give me a list that counts them all, right? So let list be an arbitrary mapping from the integers to the guys.
If you ever go to the slides again, would you be able to actually point out that this is a proof by contradiction?
No, because I shouldn't have ever said that. I hate proof by contradiction. This is proof by the game. The adversary is giving you one, right, and we're proving it's not. I mean, we could just say it boils down to the same thing. All right, so we have this list that the adversary is claiming solves the problem, and then we have to prove to him it doesn't solve the problem. Why? How do we prove it? We come up with some guy, say this gnome here. We say, look at the gnomes in the set, and we don't think you've listed him. He says, yes, I did list him. He's listed in the ith place, right? And then we prove, no, look at the ith place is mapped to somebody else. Yeah.
So where it says for all lists under uncountable, does that mean for all members of the list or for every list?
For every list.
So why is it for every list for uncountable and then there exists a list for countable?
Because the one is the negation of the other. How do you negate something is the for alls turn into exists. Right? The font's different. This one has black lining, but there you have it. Yeah?
So when we added the gnome at the end, there was no last bit number to associate with it. Is that the reason why we can't?
Yeah, so here's what's confusing is if you think, when the adversary gives me a list, he only gives me a finite part of the list. And then when I say, hey, you didn't list the gnome, he can say, oh, funny you should mention the gnome. He was going to come next, right? So we can't, that doesn't seem fair, right? So we make him give us the entire list, which is infinite. And then we say, you didn't list the gnome. And he said, oh, I meant to list the gnome, and he slips him in, but it's too late because he already gave us the list.
Countable, if you ask him like a list, an infinite list.
Exactly.
It's not like we can find the value we want in an infinite list.
Exactly. So here we're going to prove that the reals aren't countable, right? Come up with a list, an arbitrary list. And what's this list? Here he gives us a list. There it is. He says, what real number is mapped to 1? What real number is mapped to 2? What real number is mapped to 3, right? He gives us this infinite list. And of course, it's infinite this way and it's infinite this way, right? It's a big list.
And these are real numbers, right?
These are real numbers. That's why it's infinite this way. It's because they're real numbers, and so they have an infinite decimal representation. All right?
Why do you add natural numbers? Like if you want to add to the real numbers at the top?
You could put 7 here if you want. 7 is a fine example of a real number.
Okay.
Right? And then its decimal expansion would be 7.00000. Yeah.
Can you just like an argument for proof say that if you could generate like real numbers by infinite bisection.
Can we finish this proof first? Let's do this proof. Do you have a question about what we're doing so far?
Yes. For like r is bigger than n, it like proves that one is the red. What does this line do? The red line up, the red one?
The red line is saying we're proving that the set of real numbers is it should be equal, it's bigger or equal to the set of natural numbers. Oh, actually, no, not equals. We're proving it's strictly bigger than. We're proving that it's not countable. It's strictly bigger than. There are more real numbers than there are natural numbers. All right? And why is that? As well, if you thought there was the same number, you should be able to list them. So here's a list. Right? An adversary came up with a list. And now what I'm going to do is I'm going to construct a real number that's not in the list. Right? And for it to not be in the list, it can't be, I'm going to come up with a number that's not this number, and not this number, and not this number, and not this number. Right? So let me tell you how I'm going to construct it. It's called the diagonal proof. I'm going to look at the diagonal, and I'm going to take the first digit after the decimal place of the first number, and it happens to be a 3, so I add 1 to it and get 4. Right? And then I'm going to look at the second digit after the decimal place of the second number, and I'm going to add 1 to it, and that's going to be my second digit. And so on. 9s are going to wrap around to zeros. Right? And we're going to just keep doing that. See here, our 9 wrapped to 0, our 9 wrapped to a 0. And we keep doing that. Right? Everybody see how we constructed this real number? Yeah?
Why do we add a 1 to the digit in the diagonal? Couldn't we just keep it as diagonal? Wouldn't that not be?
No, because I want it not to be this number. How do I know that the number I'm producing is not this number? Well, it's different in this place. Right?
Can you just make it up?
Did I make this up?
No, can we just make up the number? Instead of 12.34 whatever, it's 12.33.
Yeah, but of course this is an infinite thing, so how do you make up an infinite thing? Yeah, it would be a lot of work. You'd be here all day, making up an infinitely long number. Right? He gave us this infinitely long list.
So that diagonal just counts for the whole infinite as it going.
We just counted from...
Vertical. The elements of numbers keeps going down.
Yeah. Yeah, so everybody gets how we got this real number? All right. Yeah, no?
But why diagonal?
What?
Why diagonal?
Well, because it works. Let me show you why it works. If you understand how we got it, now I want to prove to you it's not in the list. Why is it not in the list? If you claim it is in the list, then where is it? You say, oh, it's at location I. Right? Then I claim, no, actually, it's not at location I. How do I prove you it's not at location I? Well, it differs in the ith location. Right? That's why we use the diagonal. We needed for every integer a different proof that it wasn't that integer.
So this proof just ensures that it's unique and different.
It's unique and different. This is a brand new real number that's not in your list. You try to list them all, and here's a brand new number that's not in your list. Yeah?
Can you use any arbitrary number rather than 1 for the addition? So
Yeah, we're going to do that later when we're going to do similar proofs, and I'll just say, take the diagonal and change it. I don't care how you change it, you just change it. And it didn't even have to be the diagonal, right? You could do some other pattern as long as every number has a different location. Yeah. Other questions? Yeah. Yeah, the ith, I know that my number I made here is not at location 5 because the fifth digit are different. Right? How did I construct this number? I constructed it so its fifth digit is different than the fifth digit of the fifth number.
It's going to the end of the list, right?
So,
The diagonal is going to the end.
yeah, the diagonal goes forever. Did that answer your question? No?
So it proves that it was
Yeah, it just
different.
didn't click.
Did it click now?
No.
No.
So the ith digit is differs. So when we look at 3, which is the 5th digit, when we look at the one above it, which is 9, go down. Oh, number 5 is 4. Yes. Sorry.
Right, so my number I made is not the first number because it's different in the first place.
But the 0 is in the second place, which already differs even more.
Yeah. It's not the first one because it's different in the first place. It's not the second one because it's different in the second place. It's not the third one because it's different in the third place.
Would it be an easier proof if you sort this list and take the bisection of any two numbers?
Why does everybody want easier proofs?
That's an easier proof.
Cantor came up with this proof hundreds of years ago, and we've all been happy with it.
Well, every teacher wants a harder proof.
Everybody, yes. I think this is you're probably not going to come up with a better proof sitting here.
Why can't it just be a vertical line? Why can't they the same digit?
Oh, because let's suppose the diagonal, the vertical is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, how can I make it different than all of them? Right? I want this to be different than everybody that you're choosing. Right? But certainly here I could say, oh, I can cover all of these because they're all different. I could make this a 4 and all of these are covered. And then I could be more efficient. But we have lots to play with, so it's not like this works, so why get excited about something else? Yes?
For the diagonal numbers, if you follow the diagonal line, for example, from mod 10, what would help with that? Right here,
Mod 10?
yeah.
Well, that's just to wrap the 9 around to 0. It's just to make it different. It could have been subtract 1. You just got to make it different.
Right, but if you follow the diagonal line, and say if the number is 9,
Yeah.
so then if it doesn't wrap around and becomes 0,
Yeah.
okay, so that's what you're saying.
Yeah,
I get it.
these 9s turn into 0s. They just needed to be different. Yeah. Wait.
It makes it 2, I guess.
Plus 1?
What?
Like, isn't it kind of like tedious to do plus 1? Or it doesn't matter.
If you get bored, you could add 2 once in a while. Yeah. Yeah, you just got to change each guy in the diagonal needs to be changed. Doesn't matter. Any other questions about this? Yeah?
At the end, how do you finally prove that number is like, how do you finally prove that it's uncountable? Just the last time.
All right, well, you claimed this counted them, and I found a real number that wasn't in your list. So your list is bad. Right? And we played the game, and I won. Right? Everybody buy this proof? Bought. Sold. Excellent. You guys have fun. At least we got a block here that understands it. Yes?
How do you check that number is not in your list?
How do I check? Well, because you tell me where is it in the list. You say it's in the ith place, and I say it's not in the ith place because it differs from the ith number in the ith location. Everybody good?
I don't know why we're checking it. If we had to 3, it's already different than the I.
Yeah, there certainly are more efficient ways of doing this. If you've already made it different, then you don't have to. But this is just nice, one clean definition. We don't need anything so complicated. All right, so in case I make you write up a proof formally, here is it written up formally. You can read it on your own. I think we've said it all. It just says what I've just been saying over and over again. All right, so let's have a conclusion about what we know so far. The integers, each integer is defined by a finite string. Each fraction is defined by a finite string, and hence they have the same size. Each real appears to be defined by an infinite string, so there are more of them, right? The set of all finite subsets of the integers, so these are the finite subsets, they all have described by a finite string, so, and hence the set is countable. But if you look at the set of all possibly infinite subsets of the integers, then it's easy to see that there's a one-to-one mapping between them and the reals. And I've often had questions on tests and assignments to prove this kind of stuff. So how do you show that the set of possibly infinite subsets of the integers is, right? There you go. They're the same size as the reals. But as you see from the title, we say there's an infinite hierarchy here. So there's finite, and then there's countably infinite, and then there's the size of the reals. This size is often called omega, and this is called 2 to the omega because it's the subset of the integers. But don't worry about that. So here, what about the reals? So any set of finite subsets of the reals is going to be the same size as the reals. But if you look at the set of all possibly infinite subsets of the reals, arbitrary subsets of the reals, then that's going to be bigger. That's going to be bigger. In fact, I have a little brother who's basically the same age as my son. He's like 26 or something. And he was studying set theory at U of T. And set theory is all about weird properties of arbitrary subsets of the reals. And my dad and I, who are both mathematicians, said, dude, that's way too esoteric to get a job. Go do something else. So you might as well be studying, Greek poetry. But then again, you guys are studying it. You guys might as well be studying Greek poetry. Just to let you know, I was walking through to get these assignments in the computer science building, and I ran into the person who's currently the head of the undergrad curriculum committee, and he said, Jeff, how are you? And I said, I'm tired. And I said, it's demeaning to teach at 9 in the morning, 2001, to a class that doesn't understand it. Now, I told him the afternoon class does a little bit better, but still, I think this course is too hard for second year. And I say it to him every time I run into him in the hall. And I say this course is too hard.
What did he say?
Oh, he always agrees with me. But today, the reason I'm telling you this story is today he said, be sure to come to the next departmental meeting because he's going to raise it and try to change it. So it's too late for you guys. Well, sorry guys, it's too late for you guys. I'm not sure about the people in the back. Sorry for telling jokes at your expense. Yes?
I got an email that said there's an ECS for the department of ECS, or they're inviting students to attend.
Inviting students to attend what?
To a review for ECS.
Go and tell them that 2001. Did you get it? Oh, I was thinking you got it. It's like you're on the mailing list. No, he got it. I'm with you. Yeah. So if I had my way, I would have 3101, which is the algorithms course, take up 2 time slots. A second year version and a third year version, because there's just so much material we cover in that third year course. And then I would take the useful bits of this course. There are useful bits to this course. and I would keep them. Well, I think, good question, because Frank, who's the head of the graduate committee, he knows that one of my favorite topics is parsing. And so whenever I say 2001 is useless, he says, yes, parsing is useless. And I'm like, no, parsing's the most useful thing in there. So we don't all agree. In fact, I would say every faculty member thinks that 2001 has material that's useless, but we just don't agree on which material is useless. So,
you just explain science?
Sure. Politics, philosophy, family dynamics, all are joyful.
What do your colleagues say about the topics? Which ones do they consider useful?
I think most of the theory people would say get rid of the pumping lemma. Yes. Most of them would say when it comes to a practical algorithm or practical sort of, I would learn DFAs. I would learn how to build DFAs. I wouldn't learn the bumping lemma, how to prove that something's not a DFA, right? I would learn grammars. I would learn parsing those grammars. I wouldn't learn push-down automata. You know what I mean? Push-down automatas. Now this stuff, I think everybody who considers them a mathematician should know it. It's way cool. When Cantor was one of the first people who really rocked mathematics. There was Cantor, and then later there was Gödel, who did Gödel's incompleteness theorem, and then later there was Einstein. These people were just rocking the foundations of our modern thinking. And I think you should have some appreciation for it. So the next topic we're going to do is the halting problem. And I would put this in the halting problem. In fact, I do cover this in the halting problem at the end of 3101, right? You spend a week on it. Everybody says they've covered it. Nobody really understands it, but they can go to a dinner party and look impressive when they're talking to their mom or their girlfriend. Yeah.
What about NPs?
NP completeness. Well, as it turns out, my father considers himself the father of the whole NP world, and so I would have to say that it's useful as well. And we're going to cover that after we do the halting problem.
So the NP world is your sibling? So you're sibling with the NP world?
I am.
How do you feel about it?
Yeah. I'm okay with it. All right. So there's this infinite hierarchy of infinities. How are we doing? We got another 20 odd minutes. Didn't we do this? Oh, here's it. All right, so this is just going back to another topic. Now we're moving in on the halting problem being undecidable. All right? So this is going to get a little... You might want to pay attention to this because this is exciting. All right? Yeah?
What's like the actual distinction between the reals and the infinite set, or the subsets of infinite sets of reals?
They're more subsets of the reals. One thing that I could get you to prove is that, ooh, that was loud. For every set S, if you let 2 to the S be the subset of all of them, this is all subsets of S, then this set is bigger than this set. And so if this is the reals, then all subsets of the reals is bigger, and so forth. And so then you can have 2 to the omega is subsets of the integers. And then each one's bigger than the previous. And now you're getting into set theory, which is really strange. I mean, the thing about set theory is I could state 3 things, which I'm not going to state, And everybody would agree that the first is definitely true, and the second is definitely false, and the third nobody knows, but you can prove that they're all equivalent. So I think the bottom line is, if there is a God, she didn't mean there to be infinite sets of infinite sets of infinite sets. She just didn't mean that to happen. Yes?
So what you have on the board, you're saying that the subsets of reals is bigger?
All subsets of the reals, all possibly infinite subsets of the reals, is bigger than the set of reals.
What?
That's, it's just you use the same diagonalization proof.
Okay.
Yes?
So when it says fractions each defined by a finite string, let's say fraction is 2 over 3. It's 0.6666.
Oh yeah, so that's like Herr Doctor Professor the great 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 has an infinite name,
But it's still
but he also has a finite name which is 2/3.
right. Okay.
Right? All right, so now this is what I was about to say. It's hard to lecture too.
Thank you. I can appreciate that.
All right, so listen up here. Woo!
Sorry.
Catwoman. We're going to say something really interesting. All right, the set of all Turing machines are algorithms, right? Here's the set of all algorithms. Each algorithm, what do we know about each algorithm? What do we know about each Turing machine is it's described by a finite string, right? And hence the set of them is countable. Now, let's go over to this next thing. The set of all computational problems, I claim each one requires an infinite description. Why? Because there are an infinite possible number of inputs. And for each possible input, you have to tell me what the output's going to be. Right? So there's an infinite number of computational problems. Each computational problem requires an infinite description, so there's the number of them is equivalent to the number of reals, right? But the number of algorithms is equivalent to the number of integers, and hence there are more computational problems than there are integers, and that means that most problems don't have algorithms, right? And that's cool. That's cool. What? It's logical. It was logical. Once you got Cantor and you got Turing in on the deal, then it was logical. Pre-them, it was probably surprising. All right, so everybody buy that? There's just way more algorithms than there are, way more problems than there are algorithms. All right, so that proves that there's some problem that's uncomputable, and we're done this section of slides. So we have, should I close this lecture and start a new lecture, or just keep on going?